consider the integral from 1 to x of t squared minus 4t plus 1 dt. This is kind of weird, but we can do definite integrals, so if we integrate this, the integral of t squared is 1/3 t cubed. The integral of 4t is minus 2t squared. The integral of 1 is just t. And we'll have to evaluate this from 1 to x. And here, what we're doing here is using the fundamental theorem of calculus, because that's how a definite integral is defined. When we substitute in x, we get x cubed over 3 minus 2x squared plus x. When we substitute in 1, we end up with 1/3 minus 2 plus 1. And simplifying this down, we end up with 1/3 x cubed minus 2x squared plus x plus 2/3. Right. So that's what we get when we integrate this by using the fundamental theorem of calculus. Now if we take the derivative of this, the derivative, I'm going to call this f of x for sake of ease. The derivative of this, the derivative of f of x, is equal to 2/3 x. Oops, shouldn't be squared, that's silly. I thought I said there should be 3. Let's fix this. Alright, the derivative of f of x, now that I've written it down properly, is x squared minus 4x plus 1. So notice something. This and our initial function are related. That we integrated a function from 1 to x, and when we took its derivative, we ended up back to where we started with x substituted in. This illustrates what's called the second fundamental theorem of calculus, which just links again a derivative and an integral. And there's two things to be aware of with this second fundamental theorem of calculus. If our function is on a continuous open interval containing some value a, then the derivative of our integral from some number a, in our example it was 1, to x, of our function with respect to t, dt, right, the derivative of this will always equal f of x. And it's important to notice that our upper limit of integration in this case is x, and not anything else. And if we generalize this even further, if we're going to take the derivative of an integral, and we're going from a to u. So this is the case where our upper limit is some other expression besides x. It could be 2x squared, it could be 3x squared minus 5. Right? It's just something more complicated than just x. Then we can't forget the chain rule. And what we're going to end up with is our function with u substituted in times the derivative of whatever u is. Right? So ultimately, it doesn't matter when we take the derivative of an integral. Right? The derivative of an integral is the original integrand with the variable changed. And this will probably make a little more sense with some examples. So let's look at some specific examples of all this. I'll do one of them here in this empty space on the right. we'd like to find the derivative of the integral from 1 to x of the square root of t squared minus 1 dt. Well, the derivative of the integral is always what you get when you substitute, when it's going from a number, in this case 1 to x, when you substitute in our upper limit, in this case x. So I'll have the square root of x squared minus 1 times the derivative of that upper limit, in this case 1, which doesn't do anything, change anything, so we'll end up with the square root of x squared minus 1. Let's look at two more. And this is a really